Welcome to Unit 2, Lesson 8, Solving Systems of Equations. Last year, hopefully in grade 10, you might have seen a little bit of this idea when you were solving systems of linear equations, or what we sometimes call linear systems. So in general, a system of equations just means more than one equation that connect together with the same variables. When we solve a linear system, or when we solve any system of equations, we were trying to find a special x and y combination, a special coordinate that would work on both of our relations at the same time. So last year when you did that with lines, you were looking for a special point that lies on both lines at the same time. Here we're going to take that a step further, and instead of just looking at linear systems, we're going to look at linear quadratic systems. And the name implies exactly what it is. It's a combination of a linear relation with a quadratic relation. So essentially we've got a straight line and a parabola. And if we're looking for the solutions that connect them, we're looking for the points where they intersect. And we can start to imagine there are three basic categories of solutions that these will fall into. One situation, as we can see here, is that we might find that there are actually two separate points of intersection. And we can clearly see, for example, that that's where those are. So if it crosses clearly through both of the branches of the parabola, we'll have 2 points of intersection. But sometimes it might just touch the parabola at one specific point, but not actually cross through and touch both branches. So it is possible that we could just have one point of intersection if it just touches at one specific point. But of course, it's also possible, depending on where the line is in relation to the parabola, that they may never actually cross at all. And so you can see here, these blue and red lines will never cross one another. And so it's totally possible that we'll have no point of intersection. We can also notice that this is sort of similar to the three basic scenarios that we would come up with when we're trying to solve a quadratic equation. When we're looking for the roots of a quadratic equation, sometimes we find that there are two real roots, sometimes we find that there's really only one real root that repeats itself, and sometimes we find that there's actually no real root at all, maybe just a complex root. So keep that in mind, because that's going to be strongly connected to the types of algebraic solving that we're going to do below. So let's get to actually solving these. So remember, solving a linear system means trying to find that special x and y coordinate combination that work in both relations at the same time. So we're going to do that algebraically, but we should be able to illustrate this graphically and show exactly why those points that we've identified actually work. So if we look at our two relations, last year, if you did learn about linear systems, then you might have learned that there are two main ways that you solve them there, which was substitution and elimination. Now, elimination does not work so well with linear quadratic systems, but turns out the substitution rule is one that works quite well. And it's actually going to work very well in this particular case, because both of these right now are solved for y, or in other words, y is isolated in both of those situations. And remember, we're looking for a coordinate that's going to connect together the x and y's that are in each of the two relations. So let's start connecting these together through substitution. For example, I can say that everything I have on the right side of this top relation, well, it's equal to y. But I also know that this y down here must be the same y for the special points that we're looking for. So really, if that right side is equal to y, then I can take it and substitute it in and replace the y that I have on the left from the lower equation. So if I number these, I'm going to call the top one equation 1, bottom one equation 2. Really what I'm doing, just to sort of explain my work here, is I'm substituting, or I'm subbing 1 into 2, subbing the information that I know from equation 1 in place of the variable it's equal to in equation 2. So that means all the stuff on the right side from equation 1 is now on the left side, negative x plus 3, all squared, and then plus an extra 2. And that's equal to still 3 over 2x plus 4. So it's like I've taken the two right sides of the equations and set them equal to each other. But now what do I have? Well, I've got an equation that involves x. That's the only variable that it involves. And I can see from the squared on the left side that it's going to be a quadratic equation. Well, that means I just need to apply all the normal skills that we would if we were solving a quadratic equation. So I'm going to expand this stuff out that I have on the left side. So that'd be like negative, after a little bit of expanding, negative x squared minus 6x and minus 9. So that's after I also distribute in that negative sign. But then I still have to add 2 to that. And it's equal to the same stuff on the other side. If I simplify a little bit, I end up with something like this. And now I do want to continue trying to collect like terms and get this into standard form, so everything together on one side and 0 on the other. But remember, in standard form, we also don't want any fractional coefficients. So one thing I'm going to do right now at this next stage is think about just taking everything in this equation and multiplying it by 2, doubling every term. So negative 2x squared minus 12x minus 14 is equal to, and now we can say just 3x plus 8. So we've gotten rid of that fractional coefficient that was there. And now I'm going to move everything over to the right side, so I have 0 on the left side. And if you run into a situation where it does not factor, then you can always try in a situation like this using quadratic formula. In this case, this one actually does factor though. Factors into 2x plus 11 and x plus 2. So just sort of jumping to our conclusions from there, we can say this one leads to x equaling negative 11 over 2 when I rearrange that little factor. And this one is going to rearrange to x equaling negative 2 when I rearrange that little factor. So let's step back and try and think about what we were trying to do here. We were trying to solve the linear quadratic systems. Well, again, that means we're looking for x and y coordinates. We're looking for points where they would intersect. Well, here we haven't found x and y coordinates, we've just found x coordinates. So we found 2 different possibilities for x values. Each of them has a y value that goes along with them. So we need to take each of them and substitute them in separately and find the y value that goes with each one. So that's what I'll use this space up here for. So I'm going to sub x equals negative 11 halves into equation 2. And I'm going to use equation 2 for all these substitutions just because that one is an easier one to substitute into. There's less calculation going on. So it tells us that our y value is 3 over 2 times negative 11 over 2 plus 4. Which really, because we know we're going to have to do some fractional math, let's remind ourselves that this is like 4 over 1. Negative 33 over 4. Added with, this can become 16 over 4. Negative 17 quarters is the y value that goes with it. So that's one of my y values that goes with one of my x values. So they are going to combine together to be one of my points of intersection. But I have another one I have to sub in. I have to sub x equals negative 2 into that same equation. So that's really just y equals negative 3 plus 4. Or y equals 1. So let's put all this information together. So I can say, therefore, the line intersects the parabola at 2 points. So I need to list them both. At the points negative 11 over 2, and that went with negative 17 over 4. And the other one was a bit simpler, negative 2 and 1. Those are the 2 points where the lines intersect. So I want you to take a minute now and try and graph both of those. So we've got a quadratic that should be fairly straightforward to graph because it's in vertex form, and a line that should be even easier because it's in just y equals mx plus b form. So graph that now, so pause the video at this stage and then restart it to see how mine went, and we'll talk about it. So here's how mine worked out. You can see for something like this, when you're doing more than one relation on a graph, it's really important that you label each one separately. So make sure we label with their equations, as you can see I've done for each one. And then we can identify what those points of intersection are. And one we can clearly see sort of exactly on the graph that we nailed it, which is the negative 2 and 1. The other one, you'll more have to be a little bit more approximate with sort of seeing it on the graph, but we know algebraically what its actual coordinates are. So this other point where they intersect, I can clearly label it. Remember, negative 11 halves is essentially like negative 5 and a half, which you can see roughly on the x-axis. That's sort of what that corresponds to. And negative 17 over 4 is roughly about negative 4 and a quarter. So mine's more like negative 4 is just because of where my parabola sketch ended up being. But that's why, in general, we only want to actually solve these exactly using algebra, but we should be able to graphically understand and visually see what's going on using the graph. So it's still important to get practice graphing it so you can illustrate. Let's try another problem. So this next one says, without solving, we actually just want to determine the number of points of intersection of the quadratic and linear relations, the two that are given there. And we're going to use the discriminant in order to do that. Once we work this out, we're going to then just illustrate it graphically to make sure that we've figured this out correctly. So first off, let's just rewrite the two relations that we have. And I'm going to call these equations 1 and 2. And once again, let's use a substitution technique. So if all of this stuff on the right side of equation 1 I'm told is equal to y, then that means I can replace it with this y. So once again, it's like I'm subbing information from equation 1 into equation 2. So we have 3 equals x minus 1 squared. Instead of just y, I'm replacing it with x minus 1 squared. And now, once again, we need to expand this out and simplify it down so that we get it into standard form. So we really need to multiply those together first. Once we expand those two brackets by multiplying them together and then expand that negative sign in, we'll end up with all of those terms that I've written down below. Now we can do a little bit of combining and rearranging. So negative x squared plus 3x minus 1. And now I'm going to move everything from the right side over to the left side. And then when I combine those two constant terms, I'll have positive 4. So what does that mean? Well, we want to put this into discriminant. Now, normally, discriminant would tell us how many solutions a quadratic equation has, and really that's what it's going to do here. It's going to tell us how many solutions this equation that we came up with has. But where did that equation actually come from? Well, it came from combining the other two relations together. So we're going to use the discriminant here to see if that green highlighted equation has any solutions. But what that's really also telling us is whether or not these two relations actually have any points of intersection. So that's really what we're checking with our discriminant here. So the discriminant, remember, is b squared minus 4ac. So that's equal to negative 3 squared minus 4 times 1 times 4, or 9, subtract 16, negative 7. And as usual, the 7 part is not so important. It's the fact that it's negative that's really important. So we can say, therefore, this special discriminant value is less than 0. Therefore, this equation that we came up with has no real roots. But remember, that equation we came up with was really something we formed by combining the two relations together. So overall, this is saying, therefore, the line does not intersect the parabola. So I leave it to you to try and graph those two relations out. I do want you to take some time to try graphing them out, though, to prove to yourself that the two relations do not cross each other at any point on the graph. But I'll also just make a note that when you do go to graph, equation 1 is pretty straightforward using vertex form graphing, but when you do equation 2, remember that's just a linear equation, you're going to want to rearrange. So you're going to want to rearrange it to graph so that it's y equals x minus 3. So if you rearrange that equation so that that y is all by itself, and so y is positive, that puts it into slope-intercept form. And if we rearrange in that case, we'd be able to graph. So I want you to try and graph it, and you can always check to see if you've done your graphs correctly using the completed version of the note. So those last two examples were linear quadratic systems, ones that involve the combination of a line and a parabola, but we can actually use these same techniques to solve a couple other different systems situations that don't necessarily involve just lines and parabolas. So for this one here, we're going to do the same thing where we're solving algebraically, and then I want you to try and illustrate it graphically afterwards. But let's do some of the algebraic work together here. So now we can see this second relation is actually still just a linear relation. So nothing strange there. It's just written in more of a standard form for a linear relation. This top one, though, x squared plus y squared equals 25. So depending on how far you got with things in grade 10, you may or may not remember that is the equation for a circle. So that actually is an equation for a circle with a radius that has the square root of this number here. So it's actually a circle of radius 5. That's what we're dealing with. We're going to try and just solve this the same way, though. We're going to just call this equation 1 and this one equation 2. And we're going to now have to rearrange one of the equations so that it has a variable isolated. Again, that's just the same way that you always have learned how to do substitution. So that's a little bit easier to do with equation 2. So I'm going to rearrange 2 for y. So in other words, it's like I'm solving it or getting y all by itself. So if I start with 3x minus 4y equaling 0, negative 4y must be negative 3x. Or in other words, y must be, well, the negatives are going to cancel one another out when I divide, so it's really just 3/4 times x. So what does that mean? Well, it means this part, 3/4 times x, can be substituted in, not into that equation, can be substituted into this equation in place of y, because now we know that it's equal to y. So we're going to sub y equals 3/4 x into equation 1 now. So now it's x squared, and instead of plus y squared, it's going to be plus 3/4 x all squared, and that's still equal to 25. And even though we started with a situation that was not just a line in a parabola, it was a line in a circle, we still arrive at this situation, which is now just another quadratic equation that we're trying to solve. So that's going to be 9/16 as the new coefficient on this other one, still equaling 25 on the other side. But remember, in our equations, if we can, we always want to get rid of any fractions. So I'm going to just multiply this entire equation, everything on both sides, by 16. So I can say, for example, 16x squared plus 9x squared is equal to, and then 400 is what I have on the other side. 9x squared. And then the 2x squared terms can be combined. 25x squared equals 400. Divide both sides by 25, and x squared really is equal to 16. Or in other words, x is equal to plus or minus 4. So again, that's giving us two x values, two possible x values, which means there's got to be a y coordinate that goes with each of those two x values. Or in other words, we have 2 points of intersection. So again, I'm going to leave this one for you to finish off, and I'll leave the graphing for you to do yourself as well. But you can just always go back to the completed version of the note and see how it is graphed and verify that you did it correctly. But just to kind of get you started with the last step, remember you're going to have to sub x equals -4 into really either of the equations, but it's easier if you substitute into equation 2, and then you'll solve for the y that goes with that. And then separately, you're going to have to sub x equals +4 into, once again, it's better if you use equation 2. So take some time to do that, find the y values that go with each x value, and then graph it, and as usual, go back and check it using the completed version of the note. For this last example, once again, we're not dealing with a linear quadratic situation. We're actually dealing with a quadratic and quadratic situation. Both of these are quadratic equations, and you can verify that if you just look closely at them. So I'm going to approach this all in the same way that I was approaching everything else. I'm just going to call this equation 1 and equation 2. And because both of these are solved for y, the idea is that I can take everything that I have on the right side of the first equation and replace the y that I have on the left side in the second equation. I'm substituting the information from 1 into 2. So that's our new left side. And on the right side, I have x squared minus 4x plus 3. And now hopefully you're getting a sense of the process. I'm trying to just take this large and complex looking quadratic relation and expand and simplify it however I need to get it into standard form, which I can then try and factor or put into quadratic formula. So before I even go too far with this at all, I'm just going to get rid of fractions by multiplying everything in this equation by 2. So negative x squared minus 2x plus 3 equal to 2x squared minus 8x plus 6. Then I'm going to move everything over to the right side. And first off, before I even think about doing quadratic formula, I need to see if this factors. And even before I think about doing any kind of trinomial factoring, I should see if it common factors. And I can common factor out a 3 to make all of these numbers and coefficients that I have inside my bracket easier to work with. And now I look at that new bracket I created and see, can I factor that, break it down even further, and avoid using quadratic formula? And it turns out we can. It's actually just x minus 1 times another x minus 1. So where does that lead us? Well, we can say therefore x equals 1. This one's telling us therefore x equals 1. So we ended up with these two separate factors, but they told us the exact same thing. So really, we only have one specific point here because we only have one specific x value, even though it just happened to appear twice and repeat itself. So this is going to be a situation where we actually only have one exact point of intersection. In order to finish that off, though, we need to finish by solving. So we sub x equals 1 into either equation, but I think it's a little bit easier to avoid fractions if we substitute it into equation 2. So our y value would just be 1 squared minus 4 times 1 plus 0, or plus 3. So 1 minus 4 plus 3, we get a y value of 0. So therefore, the parabolas intersect at just this one single point, 1, 0. Just that one single point. Take a minute now and try and graph those two quadratics out, and then I'm going to just jump ahead and just finish by showing you what mine looks like. So try and do it independently first, pausing the video at this stage, and then I'll show you what mine looks like. But just keep in mind, you will have to do a little bit of extra work in order to graph these. So this is a good lesson to review a lot of the skills we've built up over this unit, because each of these are in their standard form, and if we want to graph them, you'll need to first complete the square and get them into their vertex form so that they can be easily graphed. So do that first, graph them out, and then restart the video so you can see how mine looked, and we'll talk about the result. So here are the results that I got for mine. And you can see that what used to be equation 1 has now been put into a vertex form that looks like that, and so that's the red one that's now pointed upside down. And what used to be equation 2 has now been put into vertex form like so, and that's the one that's in orange. And we notice that there is just this one specific point that I've highlighted in purple and just made note of there, where even though, because of my very rough graphing here, my very rough sketching, it does look like there's a few points where they touch, but really, if we were to zoom in really close on more exact graphs, we would actually see that they only just touch at that exact point, and even though they're really close everywhere else, they're only officially touching at that one specific point that we found, 1, 0.